is a pain.
I've turned on the audio. Oh, there's a waiting room.
Admit the people.
Yeah, let me turn that off. Okay, they're in.
All right, we're currently doing like a technical sound test for anyone who's just joined the waiting room. And I have a microphone, which feels very dramatic. I am still doing a sound test. Yes, no, maybe, I don't know. Okay, that's true. That's true. I'll hang tight. We will kick off shortly. I'm going to grab my laptop actually as well.
Oh, actually, this is just haven't seen those slides. But
Yeah, it is.
okay, lovely.
Like everything is self acknowledgement, but I think I can just say.
Great, we should be chilling. No? Why did that? There we go. Gonna
Alrighty, how are we tracking? Have we done a sound test? Great, awesome. I assume the sound is good. If anyone on the chat can't hear me, say so now, because it will not get better. All right, we're just waiting a few more minutes for people to arrive in the waiting room, and then we're going to get started with the beginning of the course content, which is very exciting. And I'm mostly just buying time right now as we set up. Hey, hey, Linga, how we doing? What's that? That's cool. I'm in it to win it, guys. Locked in. So excited. Yeah, it's pretty miserable. I actually drove today. I usually ride to uni, and I was like, I cannot bring myself to ride in this weather. So I copped an $18 all day parking ticket. Well, it's not like a fine, but it's like paying $18 for parking is miserable, but less miserable than riding to uni in this weather. We're good? Great. All right. So I'm assuming everyone can see the slides. Lovely. All right. So welcome to the Database Systems workshop run by CISSA. So I'm Lucy Martin. I'm a tutor for this subject. Nothing I say is necessarily endorsed by the uni, but let's kick off with today's content. All right. So they are doing some things, and we are holding tight. Alrighty, so basically there's a disclaimer on this workshop. Yes, I'm a database tutor, but I'm here in the capacity as like a peer and as like a friend. Nothing I say is like endorsed necessarily by the lecturers or the tutors of this course. And that's just so that nothing I say, like you guys can't go into the exam and be like, but Lucy said this in the workshop. And then the lecturers have to be like, that's nice. We didn't endorse that workshop. That's on you, right? So to make it clear, everything I say today is based on me as an individual. I do, however, tutor the subject, so I know a thing or two. We also have another tutor in the room, Linga. Say hi. So between the two of us, we'll answer any questions that you guys have. All right. So CISSA is a student social club. We do a series of things, including industry connections, social events, education workshops, this being one of them. And if you aren't a member of CISSA already, please join. We love new people.
So we'll get the Linktree QR code up in just a little bit, working on those details now, but we'll just move on for the time being.
All right, so every semester, CISSA runs a series of workshops for basically a number of the first and second year subjects. We've also branched out to a couple of third year subjects in the last year or two. These workshops are basically kind of like a peer revision study sesh, and it helps us, basically you as students get to ask tutors, past or present, some questions about the subject so that if you realize that you've gotten to week 12 and you completely forgot the content from week 4 or week 7, now's your opportunity to run over it and clarify what was happening there. I cannot operate in these conditions. I can hear myself through the speakers, but delayed by like a minute.
Oh, so you got the...
All right.
Yep, I know what it is. It's because we have the YouTube on.
Okay.
Good. Oh, change it.
Okay, so the agenda for today, I think that we've covered what the CISSA revision workshops are. The agenda for today is basically we're going to go back over ER modeling, then we're going to do some relational algebra, we're going to touch on a little bit of SQL, look at some query optimization, and then go into normalization, transactions, distributed databases, NoSQL, and then just some general like Q&As. And we'll be doing some questions as we go through, so it won't just be me yapping at you for 2 hours, because that's not very fun for anyone. All right, so ER modeling. Who remembers Chen and ER modeling, right? Let's start with the basics. So if I draw a rectangle, what does it represent? Yeah, love it. All right, so this is an entity, right? And an entity can be any kind of like real world concept that we're trying to capture in our model. We then also have a diamond. Does anyone remember what a diamond represents? Yep, a relationship. Well done. All right, now on top of the entities as squares and diamonds as relationship, we also have connecting lines to depict that relationship, right? So we have a few different kind of lines. If it is a line with an arrow, what does the arrow represent? That it's 1. So these lines basically depict 2 types of constraints, all right? The constraints are key constraints, and then we also have key constraints, and then we also have participation constraints. All right, so when you're thinking about key constraints, you have to think quantity, or if it makes it easier, quanti-key. Because key constraints are talking about the many-to-many, many-to-one, one-to-one relationships. You're talking about the quantity of rows in those entities that are participating in that relationship. So try and think quanti-key, right? Quantity, quanti-key, key constraint. So that is whether it's 1 or whether it's many. So when there's an arrow, it depicts that there's a 1, and then when there's no arrow, it depicts that there's many. So this is a 1-to-many relationship or a many-to-one relationship. Now, just for a quick bit of revision, in a 1-to-many relationship, so obviously there's an arrow and it's depicting that one of these entities only involved in this relationship once, right? Which entity in this diagram, let's call this A, and we'll call this one B. Which one is the one that is many and which is the one that is 1? Yeah. So the tip that I told my class is that if you picture your favorite Godzilla film, there is usually a huge crowd of people on the ground and they are all pointing to the one Godzilla, right? So the thing that is many points to the 1. So A is the 1, B is the many, right? And that also means, so we want to make a distinction here. There's the thing that is 1 and has many, and then there's the thing that is many and has 1. right? Because trying to work out which way the arrow is pointing can be confusing, but I'm hoping you guys can picture that image of basically a floor full of like people in New York City all pointing at the one Godzilla and be like, wherever that arrow is pointing, that's the thing that is one and has many. All right, so that is a key constraint. That then brings us to participation constraints. Does anyone recall what a participation constraint was? Yeah, so it's basically whether it's what we call mandatory or optional, right? So there's total participation, and that's mandatory. And there's partial participation, and that's optional. And what that means is that in this relationship, you can depict using thick or thin lines, whether or not it's like compulsory, mandatory, total participation for a relationship, for a row in this table to be in this relationship, right? So if we were to rewrite this, and this was album, and this was song, we could argue that a song doesn't necessarily have to be on an album because it could be a single, but an album has to have songs, right? So we would make this mandatory. An album has to have songs. All right, so moving on from that, we then also have special attributes, multi-valued, composite, derived, and relational, right? So if we have an entity square, right? Entities are represented as rectangles. So let's say we have a dog, and this dog has attributes, right? It probably has a name. It might have an age. It might have a breed. It could have a color. All right, so all of these attributes are helping to describe our dog. Now, we need, for every entity that we have in our Chen/ER diagram, we need to be able to uniquely identify a row, and we need to give it a primary key. Does anyone remember how to depict a primary key as an attribute in Chen's? So let's say this dog has like a council registration, right? Unique number that it's been registered to. So Rego ID. So this is a really good example of what could make a good primary key because it will be unique. And when we're trying to depict that it's a primary key, we underline that value. Yeah? Does everyone recall that? All right. So that is your primary key. The rest of these are attributes. And then, I mean, this is still an attribute, but it's your primary key attribute. Now, who remembers how to depict a multi-valued attribute? Okay, I'll give you a clue. When you have, let's say this dog is a Dalmatian, right? Actually, let's do something different. All right, so this dog is a shelter dog, right? So when the breeder bred the dog, it had a name. When the dog went to its first family, it had a name. When the dog went back to the shelter, it had a name. And now it's been adopted again and it has another name. So this dog actually has a lot of names. In fact, to the point where we might not be able to tell how many names a dog has, right? Now, usually you would have one. I think maybe I'll use languages. All right, so we'd use a different entity to make this extra clear. All right, so we have a person, and they speak many languages. Now, a multi-valued attribute, multi-valued, in order to draw a multi-valued attribute, you need multiple circles, right? So the M in multi-valued, multiple circles. That's how you're going to draw a multi-valued attribute. Now, does anyone remember the difference between a multi-valued attribute and a composite attribute? Alrighty, so let's go over it. So a multi-valued attribute means that it is uncountable. You do not know how many values there may be in that attribute, right? So this person might be monolingual. They might be Duolingo. They might speak 8 languages. They might speak 3 languages. They might speak no languages, potentially. Maybe they're just born. So we literally cannot count how many languages this person might have. That's when we use a multi-valued attribute. We truly do not know how many values in that attribute there could be. We can't count them. It could be infinite. On the other hand, we use a composite attribute. And I'm sure you've all seen this because it's been done to death. Address, street number, street name, suburb, maybe state, etc. Right? So when you have a composite attribute, what you're saying is that you have a finite amount of components that go into this one value, right? So we know that an address has a street number, we know it has a street name, we know it has a suburb, we know it has a state. And if we wanted to, maybe this is a global database, we add a country. And maybe at best we add a zip code or something, or a postcode. But we're never going to need more than those fields, right? We can capture any address using these fields, and only these fields. So it's not infinite, the amount of fields that we could potentially have under our composite attribute. It's actually finite. We can count it, we can know how many fields and how many attributes that composite attribute has. All right. Now there's another special field called a derived field. So if we have a date of birth for this dog, right, then we can derive its age. We can look at the current date, we can look at the date of birth, we can be like, all right, well, we know this dog is 13 years old, right? So when we're doing a derived attribute, right, derived, I want you to think about the D in derived for dashed. When you're depicting a derived attribute, you use a dashed line, okay? And so this is going to be the age of the dog. All right, so this is all capturing our database in logical design. Does anyone remember the 3 steps of the design phase? There's conceptual, sorry, this is conceptual design. Then there's logical, and then there's physical, right? So ER diagrams and Venn diagrams are conceptual. And then we take that into logical and physical, and we use an EER diagram, and we start using the workbench modeling. All right. So that brings us to relationships. So this is an entity. Remember, we need a diamond to depict a relationship. So let's say a person can own a dog. All right. Now, this currently depicts an optional many-to-many, which I kind of like, because this essentially says that a dog can have optionally many owners and a person can have optionally many dogs, right? Someone can have more than 2 dogs. Also, a dog might be a stray and never be owned by someone in their life, right? So that depicts an optional many-to-many, and we know that it's optional many-to-many because without the arrows, it depicts many. And because they're thin, we know it's optional, right? So what we call that is the participation constraint when it's thin, and that is what we call a partial participation when it's optional. All right, so we have a series of relationships. This relationship here is a binary relationship. Now, the reason why it's binary is because we have 2 entities, yeah? Bi generally means 2. So binary relationship, 2 entities. Now, we could also theoretically have a unary relationship where a person, little diamond, person might have a roommate, right? So a roommate is going to be roommates with another person, right? Does anyone recall what this relationship is called? If this is a binary relationship, this relationship is a unary relationship. Yeah, so unary being 1, uno, right? So you have a relationship with itself. The last relationship that you may see is a ternary relationship, which is where another entity is involved in the same relationship as two other entities, right? So this is a ternary. All right, and that's generally because the information in this relationship here requires all three entities to be able to capture what that relationship is. And they should generally be used sparingly, but if you're like, no, like all of this information, like to capture this relationship between these three entities correctly, I need to have it all in the one table, then there's potentially good reason to have a ternary relationship. All right, so that brings us to, so we've just covered Chen's notation. We're going to cover a bit of crow's foot notation. All right, so this is conceptual. And then when we want to depict it logically, we use crow's foot. And crow's foot is what you'd be used to modeling in SQL Workbench with. Woo. All right, so in SQL Workbench, you have a table. And then you have another table. Right? And then these tables have attributes. So a song will have maybe an SID, a song will have a name, a song will have a duration, maybe a genre. All right. And then an album will have an AID, maybe a name. And then what else would an album have? An artist. Technically, the song would have an artist too. Anyway, point is you can have a series of attributes, and depending on your business case, that will determine what attributes you have in each of your tables. So we now have our two tables, and in EER, we want to depict a relationship. So the reason why EER diagrams get their name as crow's foot, right, is because they have these little doodads, right? A little crow's foot. Okay, now I got to work out which way this relationship goes. So whenever you're reading a crow's foot diagram and you want to know what the relationship is to each other, you basically cover up the closest, like if you're looking at song's relationship to album, you cover up song's relationship and you go, song's relationship to album is, and you look across, right? So when you've got song's relationship to album, you know that a song can only belong to one album, yeah? So that means we're going to use one of these lines. That depicts that it's one. The other thing is, we said earlier that songs don't have to belong to an album, do they? No, they could be a single. So we're also going to make it optional, and that's when we use the little circle. Right, so this is optional one. And then on the other side, we look at album's relationship to song. So we cover up this relationship and we go, all right, album's relationship to song is an album must have many songs, right? So then the many is depicted using the little crow's foot. Sorry, my markers are dying. All right, so it must have many. And so this is the many indicator in EER, and then the must have is that solid line. So when it's optional, it's a circle. When it's mandatory, it's a solid line. And then you have your many and your one. All right, so that is how you read and model crow's foot notation. All right, now the other thing about crow's foot notation is it's really important. Primary keys are kind of critical in database systems. You need to be able to uniquely identify a row in a table at any given point in time. Now in ER, aka Chen's diagrams, we depicted our primary keys by underlining them, yeah? Now in EER, in crow's foot, our primary keys, you'll notice if you've been paying attention that in EER, your primary keys are usually a little yellow key. Now, I don't have a yellow marker, and I'm not sure if it would show up even if I did, so it's an orange one in this example. But you've got a little primary key, right? And then also, in order to capture a relationship, you need to have a foreign key. So we have something that is having 0 or 1 albums, and then we have one that has many. So when we're resolving a one-to-many relationship, when we're resolving a one-to-many relationship, there is one side that is many, has one, and there is a side that has many, is one. Right? So an album has many songs. A song, on the other hand, has one album. Yeah? So when we resolve the foreign key is always going to end up in the table that has one, right? So here we're going to add a little foreign key, and it's going to be album. All right. So does anyone know the issue? These are just all like regular attributes. So regular attributes are usually like a little diamond. If it's filled in, it's mandatory. If it's not filled in, it's optional. But does anyone know why this foreign key for the many-to one has to go in the song table? In the thing that like is many has one? Nailed it. So you cannot have lists. In a relational entity database, you cannot have lists in like a singular cell, right? Because if you tried to put, say, song in album, right? So you'd have one row for an album, it'd have an ID, it'd be, say, Taylor Swift's Reputation album, right? And then you would have a series of songs. And if you tried to put the foreign key in this table, you'd have to put all like 13 tracks of that album in that one row, which then ends up giving you a list. And lists are bad. Anytime you find a list in your modeling, something has probably gone wrong. So you need to find a cleverer way to depict it that upholds data integrity. While this one, since it is many, it has one, it makes sense that if we have, I don't know, Getaway Car, it belongs to the Reputation album, and we can put that here. If we have Are You Ready For It, that belongs to the Reputation album, and it can go on that table, right? Because it's only capturing one value. There's no list when you put it on this side. Yeah? All right. So, Crowsfoot, Chen's translating design from conceptual design to logical design to physical design, right? So, we know that Chen's and ER, so that's that little rectangles, diamonds diagram, that is our conceptual design. Then we take it one step further and we associate it with a database type, which is our entity relational databases. And then we use EER to model our logical. And then the last step to physical design, does anyone remember what changes between logical and physical design? You add data types, right? So this is still very much like capturing the attributes and the entities and the relationships. And then in physical, you start adding the fact that like, oh, SID is an int, and then name is a varchar of like 50 characters, and then duration is, I don't know, a time. All right, so that's when you add your data types in physical. Now, does anyone know the difference between a varchar and a char? Like, let's say I had this as char 4, and this is varchar 50. Does anyone know the difference between why you would use those two? All right, so char, when you say char of 4, it means that you're saying every single value in this column is going to be 4 characters and exactly 4 characters. So if you only put in 3 characters, it's still saving 4 characters in your database every time. It's just like an empty character or a space. Varchar, on the other hand, varchar literally stands for variable char. Var, variable, char, varchar. So varchar actually doesn't, if you say varchar 50, you can store up to 50 characters. But if you put in less than 50 characters, it will only save those 10 characters that you put in that value, or only save those 20 characters that you put in that value. So varchar actually overall is like smaller in your databases, but for an ID, like all of our student IDs are the same length, it makes sense to be using char because that helps uphold data integrity because everyone's ID should be the same length. All right, so that's the difference between char and varchar. All right, cool. Yeah, I reckon. Oh, wait, are there any questions so far? And then we'll go through tips. Anyone want to go over things in more detail? I don't bite. Is there anyone online that has questions? All right, cool. So the general tips for approaching these questions in your exam is do not include the actual business entity, right? So if they're saying you're modeling the Melbourne airport, don't put Melbourne airport as an entity in your database, right? It's not like when you're trying to decide entities, yes, they have to be like real world concepts or things. And they also have to have data that you want to capture about them. If you are dealing with the business as a whole, you're actually dealing with smaller components than the business as a whole. So if it's the Melbourne airport, you might be dealing with terminals or staff or planes or baggage carousels or other smaller components of that business. So generally speaking, you will not include the overarching business in your model, right? Even when it comes to things like if you have, say, a chain of stores and they're like the cinema example that we did, I think in like week 3, right? So the cinema example, you don't put the cinema chain in your database. You're actually just storing that they have multiple locations, you know, and those locations each have multiple screens and those screens have projectors and et cetera, et cetera. So avoid putting the actual business or company into your model. If you do feel like there is a small edge case where no, truly, like generally speaking, don't do it. You need to be able to ask yourself, like, what data do I need to store about this? And when you're modeling a database for a company, that company should not end up in that database. Everything that concerns that company should, but the company itself, there's no data to store about it because you're storing everything that that company is concerned with. All right. Avoid using vague words like has to label your relationships. Don't use has. Don't do it. All right. And don't also then just go, I don't know, like possessives for everything. Like mix it up, keep it fresh, give those relationships meaningful labels. Okay. They don't all have to be unique, but most of them should be, right? Like you can be meaningful and semantic about the way that you label your relationships. Do not overuse weak entities. So weak entities should only be used when they cannot exist without a parent entity, but more importantly, when they're identified uniquely by their parent entity. So in the week 3 example, when we did cinema, right, each screen had a number, right? But that screen was numbered, let's say 1 through 8, yeah? Which meant that the Docklands Hoyt Cinema had screens 1 through 8, and then the QV Cinema had screens 1 through 8. But if you went to that database and you said, get me screen 7, your database would return you 2 results. It wouldn't actually know which screen 7 you wanted. So you cannot uniquely identify a screen by itself just by using its screen number. You actually also have to then use its location, right? Like its store, yeah? Its cinema. So then you'd be doing Docklands screen 7, QV screen 7, and that is actually what's going to uniquely identify it. So in that week 2 or 3 case study on cinema, the screen was the weak entity on the cinema because it needed to be uniquely identified by that cinema. Right, so when dealing with weak entities, use them sparingly and only use them when you're like, no, this like needs to be uniquely identified by its parent or like, yeah, by its strong entity. All right, remember to annotate underline for primary key. All right, so we talked about this. Every single rectangle in your ER diagram, so these guys, these ones here with your things, they always need a primary key. Now, this had a primary key, I erased it, so we're gonna put it back, right? Rego, whatever your dog is registered as, and you need to underline it, all right? We don't know it's a primary key unless it's underlined. So when you're doing your assessment pieces, always double check that every rectangle has an underlined attribute because that is the primary key and we need to be able to see what primary key you selected for that attribute, for that entity. All right, that also brings us to dashed lines for weak entities. So in the example of the cinema and screen, right? So cinema now has a CID and that is the primary key for cinema. And it also has, say, a location. So this is going to be your Docklands or your QV or your whatever. All right. And then we also have a screen. All right. And we have a relationship. Now, this screen has a screen number. All right. But the screen number alone cannot uniquely identify the screen as we just spoke about. So in that case, it's a dashed line because that represents that it is a partial primary key. And then this relationship, so all these lines need to be bold because you've basically said that this is a weak relationship. So the relationship lines need to be bold, the relationship diamond needs to be bold. Now, currently I'm depicting that a cinema, it's optional for a cinema to have a screen, which there might be a world in which that's true, but it's very unlikely. So I'm going to also make this relationship bold too. All right, now each screen also should only belong to one cinema, right? They're not moving screens, they're like physical things. So the thing that is many points to the one, right? So that depicts that weak entity. And so this means that when you're resolving this into into crow's foot, which is EER, when you're resolving this, you're going to end up with a table for screen. All right, and it is going to have its screen number as one of those like yellow primary keys. But because it's a weak entity, it cannot uniquely identify those by itself. So it also needs the CID as a primary foreign key. All right, so that's one of those little red keys. And those two attributes together, they will actually identify a singular screen. All right, cool. All right, so who remembers what a surrogate key is? Surrogate key is a little sprinkled in key, right? So you can use surrogate keys if you can't find something that's going to uniquely identify your entity, and it also doesn't make sense for it to be weak, then you need to basically come up with a surrogate key, which means you fabricate a key and it'll just be a unique number that really only is important for being able to uniquely identify in your database. So one example is, I mean, dog rego kind of makes sense because we have to have registrations for dogs and those would be unique. But for song, a song does not have a unique ID necessarily, right? Like, it's not like we refer to songs by unique IDs. We added SID as a surrogate key because there's potentially songs with the same name by the same artist. Example, Taylor Swift, who re-recorded all her songs, but they're pointing to two different songs, right? So that's when we come up with a surrogate key and we just like sprinkle in a fresh new key to uniquely identify those rows in that table. Does anyone have questions on what a surrogate key is or does? All right, we kick on. So proper use of relationship attributes is helpful. So if you have a relationship attribute, so basically relationships can have attributes. I'm trying to think of what a meaningful relationship attribute for this would be. Cinema has a screen. Can't think of one. But you can give your relationships attributes. And when you resolve those attributes on the relationships, they need to follow the foreign key. All right. So when we resolved this, in this table, where did our foreign key to capture this relationship end up? There's always a foreign key involved in capturing a relationship. In this example, where did our foreign key end up? Was it in the cinema table or the screen table? Yeah, it's in the screen table. This is our little foreign key. It's a primary foreign key, but it's still also a foreign key, right? So it ended up in the screen table, which means that this attribute A on this relationship, it follows that foreign key that's capturing the relationship, and it's also going to end up in screen. So screen now has an additional attribute called A. Right? So wherever your relationship attribute, like wherever the foreign key to capture that relationship goes between conceptual to logical, that's where your relationship attribute has to follow. All right, cool. Does anyone want to recap associative entities and many-to-many, resolving a many-to-many relationship between conceptual and logical? I don't buy it. Okay, well, who remembers what is an associative entity? So when you're dealing with a many-to-many in logical, right? So a many-to-many, let's erase dog. All right, so when you're dealing with a many-to-many, you've got a rectangle, a diamond, a rectangle, right? Rectangles are entities, diamonds the relationship. You've got some relationship lines. Now, when there's no arrows, this means that it's many-to-many. And when we're resolving this relationship, right? So let's say this is A, this is B. When we're resolving this relationship into EER, we have to work out where does the foreign key go. Now, in one-to-one, it's not going to matter. You can put it in either table and it'll be fine because it's one-to-one. In one-to-many, I already covered that the foreign key has to go on the table that is many and has one. Because when it has one, it means it has one foreign key and you don't end up with a list of foreign keys. So it has to go in the is many has one, right? So whichever table is doing the pointing, that's the one that is many and has one. So the foreign key, the little red foreign key, is going to end up in that table. Now, when you're dealing with a many-to-many, you're actually going to get a list no matter which table you put it in. All right, so when you have a many-to-many, if you try to put this foreign key to capture the relationship in B, you're going to end up with a list of A's. If you try to put the foreign key into A, you're going to end up with a list of B's. And as we know, no lists. All right, so we have to come up with a better solution, a smarter solution. So that's when we have an associative entity. So when you convert this into logical, you're going to end up with a table for A, a table for B, and you're also going to end up with an associative entity for this relationship. Let's call this Z, right? So you also have a table for Z. And the way that this is going to connect is we have to have a row from each of these tables, and then it can either be optional many or mandatory many. Sorry, mandatory being the line, right? So this is optional many, this is mandatory many. And again, because we read relationships by covering up the nearest one, we're saying A can optionally have many rows in Z. B must have many rows in Z. And then we're reading it the other way around. We're saying like, if Z has a row, then it has to have an A. And if Z has a row, then it has to have a B. And that makes a lot of sense if you break down what an associative entity is doing, because an associative entity is going to use primary foreign keys from its sibling tables, right? From the tables that are in that relationship. So we're going to actually have AID as a primary foreign key, as a composite primary foreign key, and BID as a composite primary foreign key in your associative entity, right? And because each row is uniquely identified by the combination of an ID from A and an ID from B, you can also never have a row in your associative entity that doesn't have both an A and a B. So it might be optional for a row, like if you have 1,000 rows in A, maybe only 800 of those rows are partaking in this relationship because it's optional. What we're saying is that if there is a row in the Z associative entity table, it will have a value for both A and B. All right, I know that that one's a bit dense, that one's a bit thick, but it's juicy. And if you want to talk about it more than happy to. All right, so proper use of relationship attributes is helpful. So yes, if the relationship has an attribute, be sure, like be comfortable. You can put attributes on relationships 100%. And then when you're resolving them, just make sure that they end up in the table that has the foreign key. So in the example of many-to-many, if this relationship had an attribute, right, C, then C has to end up as an attribute in the table Z, right? Because that's the associative entity table. That's the table that's capturing the relationship, and it's following these foreign keys. All right, cool. Next slide. Yeah. All right, so when you're reading these questions of the exam, read the question in its entirety, skim it as fast as you can, and then go back through and decide sentence by sentence which are likely to be your entities, which are likely to be your attributes. If you like underlining or highlighting or color coding, like be my guest. All right, and focus on nouns when you're trying to decide entities, figure out the relationships. So it's normally in a sentence that will have both of those. Like if you identified your entities, and they start talking about those entities together in the same sentence, you can be like, oh, there's probably a relationship that I need to capture here, potentially. All right, and then pay attention to keywords when determining the relationship constraints. All right, so some of these keywords are at least one, at most one, might, may, can, etc. Entities don't have to be physical solid objects. They can be concepts, which we talked about earlier. An entity can be just a concept in the real world. And then double check special attributes. So again, remember the special attributes? They were multi-valued, composite, and derived. All right, and then also, it's not necessarily special attribute, but it's worth double checking. Did you have a primary key for every entity? Because you need one for every entity. All right, cool. List your assumptions if you made any, but don't like lean on them too heavy. Generally in the assessment pieces, they're going to try and keep it clear and achievable because they don't want you to be too confused, right? So it's highly unlikely that you'll need to list many assumptions, but if there are any that you've made, like if it's a thought that you have, you can jot it down. Like it's not going to hurt. Just don't use your assumptions to try and like rewrite the brief because it's not going to work, all right? Okay, so do not draw a messy final model. If it's too messy and we can't read it, you can't get the points for it, all right? Like it's, please, right? Do yourself a favor and us a favor, make it clear, make it legible, right? All right, beauty. And also, please check your assignment 1 feedback. If there is anything that you didn't understand or might have been missing in assignment 1, your marker should have flagged that, and it would be worth reviewing anything in case there's something that, yeah, you're not entirely grasping. All right, beauty. So we have a practice question. We have a brief. It's the Bridgman Art Library. We're going to give you some time to work through it. Please talk to your peers at your table. I know it's confronting to meet new people, but you'll learn a lot more from discussing this with your peers than just trying to like slog it out on your own and get a bit lost and confused. So I'm going to give you some time to chat through how you would draw a Chen's diagram and ER diagram for this one. All right, thanks. Yeah, if people want to use a whiteboard, that probably makes it easier because I can see a lot of different paper. So if there's like 3 tables more or less. Right, so if this table wants to take that whiteboard over there, you guys can hop up and I'll give you guys a marker. And then come on, up to you guys. That's nice. That's it. All right, cool. So if you guys want to take this table and this whiteboard, you guys can draw out your tent there. If this back table, if you guys want to take that whiteboard in the corner there. Yep. So this back table here, you guys want to hop up, take this back corner, and then after maybe jump on the front table, which could be a little light.
Yep.
Yeah, so you guys can I'm boxing off my table there. And then well, actually, maybe use the side box, then you're not meeting. Yeah, you see. Hey, everybody. No, there are fields of life, so I'm just gonna get you guys to throw it.
Yeah, thanks.
Yeah.
We're doing for lunch.
I think we-
We're having lunch at home. Another works to go through.
Because the digital exam, that's amazing because they
Oh,
don't have
there's something for you.
so we need these skills to be able to.
Like we are hosting, but I.
Yeah, so, sorry, I'll grab you guys.
So, okay. Very good.
We lost the slide on this.
We did? Okay. Yeah, that's all right.
I'm going to have to change away from the slides for just a moment.
Yep. And owner. All right, now let's try and identify some of the relationships. So a relationship is something like customers must register a proposal, right? So now we know that there's a relationship between customer and proposal. Each artwork may have been owned by many owners. So we know there's a relationship between owners and artwork. The Bridgman records a single record. So those are the 5 entities. Bridgman records a single maker for each artwork. All right. So based on that sentence, if Bridgman records a single maker for each artwork, we know that there's a relationship between maker and artwork. If there's a single maker, we know that there's basically a one-to-many relationship, in that a single maker means that there has to be one maker for each artwork, but that maker could theoretically have made many artworks. Yep. All right. So these are the kind of things you have to be thinking about when identifying your many-to-many, one-to-ones, mandatory. Sorry, I should be more technical with that. Total and partial participation. Total and partial participation is your mandatory and optional. All right, cool. So if we bring up the next slide, we can depict those relationships. Yep. So a proposal must have one customer. A proposal is for one artwork. An artwork must have one maker. A maker can optionally have many artworks. An owner optionally can own many artworks. An artwork can optionally be owned by many owners. All right. So that then brings us to our attributes. So if we go through, we can identify the attributes based on the intended use, the duration, the date, the address, the country, the name, basically the artwork number, its width and height. And so we can build together this picture of all the attributes in this Chen's diagram. And that brings us to our final model. Ta-da! Which includes things like, the proposal's intended market and use, the width and height of that artwork. So this one here, what do we call this special attribute? Yep, this is a composite attribute, correct? Why is this line dashed? Yep, because artwork is a weak entity on maker, right? So an artwork is uniquely identified by its maker. It's very important when you depict a weak entity that you bold the relationship line and the relationship diamond, because artwork actually has 3 different relationships. And if you're saying that it's a weak entity, we need to know which relationship it's weak on. And by making the diamond bold, that tells us you mean that it's weak for maker. The double circle, so this is a multi-valued attribute, right? So M, when there's multiple circles, it's a multi-valued attribute. And a multi-valued attribute is when it is not countable. So this person might have 0 phone numbers. They might have 1 mobile phone number. They might have 2 mobile phones and a landline. They might have a work phone, a personal phone. There could be any number of phone numbers. We don't know how many numbers they have. And because we don't know how many they have, it's uncountable, it's like infinite. So we make it a multi-valued attribute. And when we resolve these, we make lookup tables in logical and physical. And a lookup table is just a really smart way to store a list. But yes, so you end up with another table here, and that will be basically the customer's primary key, which is ID. So the customer's ID, and then a phone number, and there'll be like a separate table when you're resolving a multi-valued attribute. So you start with a multi-valued attribute in logical, and then you spin it out into its own table in logical and physical. All right, cool. So that brings us to relational algebra. So relational algebra is the formal kind of like understanding of what SQL came to be. This is what SQL was built off of. And it's basically a way of expressing joins in sets. So you have selection, which is sigma. That's the little loop-the-loo. And then it selects a subset of rows. So that is horizontal filtering. Right? So your selection might be, I want all students with age 19, right? So then from a row of all the students in this classroom, you're only going to get a subset of the entire row of a 19-year-old student in this classroom. All right, projection, pi, retains only the wanted columns from the relation. So rather than saying, I want all students in this classroom and I want to know everything about them if they're 19, you can be like, well, actually, I really only want to know the names of everyone in this room. Right? So you can get all rows from this database, this figurative database that we're talking about, and you can just return all the names so that I can see who's present today and I could address you by name. All right, then you have union. So tuples in one relation or in the other. So a union basically takes, so set notation is done basically kind of like as a Venn diagram almost. I gave out all my markers. All right, so set notation. You've kind of got this, right? So you've got union is a version of that. Set difference is a version of that. And then there's cross product, right? So let me just bring up the slide. So union is going to be everything. So it's like all of this, all of this. Then there's set difference, which is basically just this little bit, right? You're looking at the difference in between the two sets. And then lastly, you've got cross product. So when you're looking at relational algebra, there's some fundamental operators. Cross product is one of them. And when you're going on to do things like intersect, then you're actually using a cross product under the hood and then like selecting based off that cross product. All right, so in the next slide, we have a series of tables for a role-playing game, all right? So you've got a player item, and an item table. And we're going to use relational algebra to return the names and values of items bought by players with experience level adventurer who are not named Colton. All right, so let's have a look at what that's going to look like. Okay. So we're selecting the item name and the value using projection, right? Because that's going to get us back columns. Then we're using sigma, which is going to select the rows. So we know that we only want the rows where the player's experience is adventurer. So we've got the row where experience is adventurer and that their name is not Colton, right? So that is the rows that we're going to get back. These are the columns we're going to get back. And then lastly, we join the tables together because we need different information from each of these tables. So we need in player, we need to know their experience so that we only have experienced adventurer. In player, we also need to know their name because we want to avoid rows where the name is Colton. And then in player item, we need to return that column and we need to return that value. So we need both of these because player item is what joins these two tables together. So we joined all three tables, then we selected the rows we wanted, and then we selected the columns. I would highly recommend when you approach these questions in your exam to start from joining the necessary tables together. Then after you've joined those together, you can select the rows that you want. And then after you've selected the rows that you want, you can return the columns that you want. So working from kind of like the inside out, I think is a more logical way of breaking down relational algebra questions. Okay, next. All right, so let's try this one together. Don't click. All right, cool. So find the names which are shared by at least one player and at least one item. All right, so we need to select the names. Where's the eraser? All right. So we need to find the names. So we know that we're going to use pi to return the names column, right? Yeah, because we need to be able to project the names column, which is shared by at least one player and at least one item, right? So now we need to select the rows where we're going to select the rows where the name is both the item name and the player name, right? Yeah. So we could do this in a few different ways. We could join all three tables together and then just select where item name equals player name. Right, and we would join all three tables together. So player, join player item, join item. But you also could just as easily join on the condition where the player name equals the item name, because that would only get you back, like that join would only be successful in the rows where they matched, right? So there's another way you could write it where you return just the names where the player player name, player, is equal to the item name. Right? And there's also one other way that you can complete this question, and that's using the intersection operator. So you would be looking at, again, the names of where player name from player is intersected with the rows. So again, we're selecting out the item name from the item table. All right, so we've gone through and we've selected the names from player name, the names from item name, and then we've intersected them. So when they join up, that's when we'll add those rows together. So if you want to click next. Right? Now, I don't think that that's necessarily particularly intuitive, which is why I think the earlier examples are more useful and they're perfectly acceptable. All right. Continue on. SQL. All right, so SQL, again, it was built from relational algebra. And it's a querying language. So once you have all your data in your database, this helps you work out what the information is. All right, next slide. Right, so there will absolutely be SQL questions in the exam. In previous years, sometimes they make the SQL questions related to the A2 assignment. So if you're familiar with that brief, that helps you understand potentially your exam questions. This isn't guaranteed, but it's been a case in previous years and semesters. So please review the A2 case study. All right. So select is very similar to your sigma because that's selecting rows. Actually, that's selecting columns. Yep. So that's actually your pie. Select is very similar to your projection, your vertical filtering. All right. And distinct is going to remove any duplicates in the result count. And then from table A, so from is obviously which table you're getting that information from. You've got where and or. So where is your condition? So this is your selection, right? So that's saying where X is equal to 10 or B is equal to 30. And you can use both and or to get more complex queries. Group by is going to group rows together and it basically aggregates the rows. So aggregation functions are used and it will group together things. When you use group by, you have to use having. You can't use the where clause because you've aggregated those rows, right? So when you start using group by, you have to use having. You can no longer use where. Then lastly, you've got order by, ascending or descending. So obviously ascending is getting bigger, descending is getting smaller. And then lastly, limit. So you may only want 1 row or 10 rows. You might not want the whole table returned to you. So if you were looking for the top 10 rows, you would order by descending and then limit it by 10. Alrighty, continuing. Right, so natural join is a beautiful thing. Natural join is going to do a lot of the work for you. It's going to look at the columns in each table, and if it can match those columns, then it will. So if there is, say, I think in weeks, 5 and 6, we were talking about sailor ID and boat ID and like sailors reserved boats. So there is a table for the reservations that has both SID and BID. So BID being the boat ID, SID being the sailor ID. And when you join sailors reservations, you can do a natural join because it's going to join on the columns that are similar. So because there's an SID in the sailors table and an SID in the reserves table, when you natural join them, it's going to join on that common column based on its name. Then there's an inner join, which you specify the condition being joined on. So when you're doing an inner join, you have to state that this attribute in this table is what I want to join on in this other table. So one example is if you had a similar setup to your sailors reserving boats, right? But in the sailors table, they just had an ID. It's not an SID, it's just an ID, right? But in the reserves table, that column was called SID. That name no longer matches. And you can no longer use an actual join because it will not know which column to join on. None of the column names match. So that is when you would use an inner join and you would specify that the sailors SID column is going to be joined with the the sailors ID column, because it doesn't have an SID. The sailors ID column is going to be joined with the reserves SID column because they're named two different things. So you need to be explicit with specifying that those are the columns you want to join on. And then lastly, there's an outer join. So outer joins will include everything from the original table. So again, it's those Venn diagrams. Right, so an outer join will keep everything in one table and then add whatever is in this table. So it means that you end up with rows where it's like A, B, C, and then there might be like, so A, B, C might be from this table. So there's columns A, B, and C in this table. And there's columns D and E in this table. So you would get values for all A, B, and C for every single row, right? Because you're getting everything from this table and you're returning all the rows in that table, right? So it's all rows and it's all that information, right? So if you're doing, say, a left join, then you're joining this other table that has columns D and E, right? But not every row necessarily may have a value for D and E. So then you may end up with like, I don't know, every few rows have a value for D and E, and then you have like nulls, right? So there's nothing there. So that is what you get when you get right and left outer joins. Depending on the order that you join them in SQL, that will affect which table you're retaining. So if you do X left join Y is the same as X right join Y. And Y left join X and Y right join X. Right, so colors. In this left join, you're retaining the X table, right? In this right join, you're retaining the Y table. So these ones are different actually. It's these ones where Y is the left join, so it's retaining Y. And then in the right join, it's retaining X. So so these two tables, these two joins are equivalent. And then these two are equivalent. Because your outer join is basically depicting which side is going to be retained. So when it's a left join, you're retaining the left side, so you're retaining all of X, and then you're adding any possible Y rows, which is the exact same as a right join of X, because that means you're retaining everything in the right table, and then you're adding any possible Y rows. Yeah. Cool. So subqueries and set operations. So nesting subqueries are very useful. Subquery operations, so you've got a really complex question and you may need to use a subquery to help answer it. So when you're querying it, you can say, I want to get all of these things from, and then you can do a subquery, and that lets you nest a query inside a query. And when you're saying that you want to get all of it where it is in, right? So you're saying any row that is in this subquery, or you can say any row that's returned that meets the condition, or you can say all. So if all of the rows meet the condition, then return those. And then you can also say if it exists. So right, this turns it into a Boolean. It's like true if subsequent returns one or more rows, right? So that's how you nest subqueries. And then there's set operations, which are all supported on MySQL. So there's union and union all. So union is going to return all records from both inputs, and union all is going to return all rows, including duplicates, if you want them to be shown. So there's no point in using, well, I'm not sure which overrides which, but if you're looking for distinct rows, you can use the distinct keyword. If you're looking for union all, then you want duplicate rows to be shown. All right, so from tutorial 5, find the employees whose salary is less than half their managers. This question's a bit of a doozy. Does anyone, well, we have the SQL here, so it requires a unary join. So we remember from covering Chen's recap that there's such thing as a unary relationship. That person had a roommate with another person. So in this, an employee can be the boss of another employee, right? So it'd look like this. You've got boss, and then, sorry, you've got employee, my mistake. Right, and then you've got a relationship diamond, and it might be like managers or /boss, right? And then you have this unary relationship. All right. Now, I'm going to argue that this is a many to one relationship in that like an employee can only have one boss, but a boss can manage many employees. So we also have to be specific about that. So if we say that this is the one side, then we have to write labels. So whenever you've got a unary relationship, especially if it's mismatched, like a one-to-many relationship, then you need to be specific and you need to like label it, right? So this is saying the many points to the one. So this would be, this is the subordinate. And then this is the manager. All right, so you can basically do a unary SQL query by using aliases. All right, aliases in SQL are really critical, and it's critical for this question because you basically have two instances of the same table. And in order for your SQL to know which table you're referring to, whether you're talking about the employee as basically an employee or a subordinate, in this case, or the employee as a boss, you then add these aliases. Once you have these aliases, you can then say that you want the employee's boss ID, right, to be equal to the boss's employee ID. So you've used these aliases, you have two of these employee tables. You're semantically deciding one of them is the employee and the subordinate, and one of them is the boss, right? And then when you want to answer this query, you have to work out whose boss is who. And in order to do that, you need to match these two tables, which are the same table, but you've given them aliases. You need to match these two tables by looking at the employee's boss ID should be equal to the boss's employee ID. Yeah? And then lastly, using these same aliases, you can then look at if this is the employee's salary, if this is the subordinate salary, we need to check that it's less than half of what the boss's employee salary is. And that's how you would answer a question, a unary question in SQL. Right. All right, so this is a little preamble. We're going to ask some SQL questions based on this golf case study. We'll try and keep it pretty quick. But every year, golf clubs and sporting organizations, in fact, you guys can read it, and then we'll just jump into the next slide. All right, let's jump into the next slide. Sorry, we're a bit pressed for time, so we're just going to keep moving. So please write a query to return the names of tournaments played at courses in the suburb of Hefferton where Bella Sandbury ranked in the top 10. All right, so I'm going to give you all a moment to try and attempt that because passively listening will not help you. So give it a go and then we'll go through it together. Okay, well, let's start with what is the column that we're returning? Yep. Correct. Tournament name. Return the names of the tournaments. Yeah. So tournament names, and we'll go distinct because there could be more than one tournament that meets that criteria, but we only want to see them once, right? So tournament name. Tournament name. All right, so what tables are going to be involved in this query? Yep. So we're going to do a from. And we know that we're going to need course, correct? But specifically, actually, if course, the courses of the subauthoritative, yep. Yep. From courses. Yep. And then course, what else do we need? What other tables are we going to need in this query? Yep, we're going to need player because we need to know Bella's name. Yep, so player. Can we do, yeah, player. What other tables are we going to need? Yep, player competes. Actually, I might write these on new lines. Okay. Player competes. And then what other tables are we going to need? There's still another table. Yep, well done. Okay, now we have to work out how to join all these tables together. So joining player and player completes, pretty easy. We can use a natural join, right? Because the player ID in player competes matches the same column name as player ID, right? So player and player competes, we're going to do natural join. All right, and then that comes down to this line here. Now, player competes and tournament, what kind of join can we use? I reckon we can also use a natural join there too. Beautiful. All right, and then course and player, we can't join those two directly, but we can natural join course and tournament. So I'm just going to move that. It's not critical because it'll have to join on that column anyway because it's the only matching column. But just to make it super clear, course. Great. All right, so we've joined all our tables together. What are the conditions that we have to select? Right, so now we've got a where. Yep. So the course suburb has to be in Hefferton, right? So we've got course. Now, luckily in this case, there is only one column called course suburb, so we can just use that one. I do like that you're being thorough and like adding the table in it, but just to make it quick and easy, we'll just do course suburb is equal to Hefferton. All right, and then we also need another condition. So we need to know, first of all, the player's name. So we need when player name is equal to Bella. Specifically first name, right? Yeah, cool. Player dot first name. All right, so now we know that we're dealing with Bella, and then we also need to know her last name and when she ranked in the top 10, all right? So player last name. All right, and lastly, so and lastly, when she ranked in the top 10. So because we joined all these tables together and it's only going to join on player ID to player ID, tournament ID to tournament ID, and course ID to course ID, then we can just look at what the rank was for that player in that tournament, right? Because we're only looking for the rows where that player is Bella. So by the time we get back only Bella Sandbury's rows from player, that means we're only getting back Bella Sandbury's competition rows. So that means we can very easily just look at whether rank was greater than 10, or sorry, whether rank was less than 10 in terms of like she did better than coming 10th. All right. So then, and rank was less than or equal to 10. Alrighty, and that I believe is it. If you want to Yep. So we're selecting the distinct tournament names from player. We're naturally join player completes, naturally join tournament, and naturally join course. And then it's where the course suburb is Heatherton. The first player's name is Bella. Last player's name is Sandbury. And the rank is less than 10 or equal to 10. All right. Query optimization. All right. Let's hit it. Okay. So I'm sure that you've all memorized every one of these formulas, right? Alrighty, so please do your best to understand these formulas. You don't need to have them memorized, you will have a cheat sheet. But understanding what's going on for each of these formulas is pretty important. Next slide. All right, so when you're, did we skip this slide? Yeah, cool. When you are doing your query optimizations, understanding the formulas is a competitive advantage because once you start introducing things like pipelining, you need to understand where you're dropping a read in. Do people understand what pipelining is? All right, let's first cover the basics. When you're calculating the cost for your query, the cost is when you read something in from your hard drive or when you write it out from your hard drive. That's why the unit is IOs, because that stands for input output. Right? The input of reading it off the hard drive, the output of saving it to the hard drive, right? So all of your cost is going to be calculated in IOs. So pipelining is when you've bought something in from the hard drive and it's currently in your working memory. If that data is already in your working memory, you don't need to go fetch it from the hard drive. So you don't need to incur the cost of reading that in from hard drive. So what that means is all the formulas on the previous slide, not all of them, but most of them have a cost for reading in the information from your hard drive. And when you have consecutive joins, right, so you have your first join and the resulting table of that first join is already in your working memory. And when that's the case, you then can drop a read on your next join because one of your tables, which is the resulting table from your first join, one of your tables is already in working memory, so you don't need to read it in from the hard drive. And that's what pipelining is, and that's why we drop one of the read-ins. All right, so understanding, you're likely not going to be asked these questions, but if you want to test your understanding, you should be able to tell me what the 2 in 2 times n passes times n pages is in the sort merge join formula. Does anyone know what the 2 is in that formula? That is quite literally the read in and the read out. So you read in all of the pages in your database, you read in all of the pages of your database, potentially multiple times in order for you to be able to do the sort merge, and then you read it out again. So that's why you get the 2 times by number of passes times by number of pages. All right, does anyone know what the B in block-orientated nested loop join means? Yeah, so block-oriented is about buffer size. So if you have X buffer available in your working memory, it means you can load in heaps of pages in once. And you can do it in blocks. So instead of loading 1 page at a time, you might be able to load, let's say, 10 pages at a time, which means your cost would be 1/10 of if you had to do it per page. So B is the buffer size. And when you're trying to calculate the number of blocks that you have, it's basically going to be your buffer size less 2. Now, the reason why it's less 2 is because you need available space in your buffer to still be able to continue to read in and read out. So you need to keep 2 aside for the reading in and the reading out. And the rest of your buffer can be used to store your database pages. All right, so buffer size less 2. And then it's going to be the number of pages in your database over the buffer size less 2. And that will tell you how many blocks you can do it in for your block nested loop join. All right, what is the 3 in the hash join formula? Right, so the hash join formula is basically that you would have seen 3 times by number of pages in, I don't know, R, and then plus the number of pages in S, right? You've seen this, right? So this formula is actually depicting that it's 2 times the number of pages in R plus 2 times the number of pages in S plus the number of pages in R plus the number of pages in S. Now, this is a much shorter way of writing this, right? But this is clearer about what's happening. Because when you're doing a hash join, these two first steps is hashing the database rows, right? And this last plus the pages in this plus the pages in that, that's actually the joining. So when you're doing a hash join, you're doing the hashing and the joining. So what's happening in this step here is you're reading in all the pages in one of your tables, you're hashing it into buckets, and then you're reading it out. So that's why you've got the two, because that's the read in all the pages, and the other part out two is the read out all the pages, right? So read in is one, read out is the second. And that means that you've sorted your first table into buckets. And then you go back and you do it for the second one. You read in all the pages in S, you sort them into little buckets, and you save out those buckets, right? So that is the 2 times number of pages in S. And then lastly, because now everything's sorted into buckets, you can basically just read in those 2 bucket files, knit them up, and you've joined your 2 tables using hash join. When you have your formula written like this, and you go to pipeline, if you just drop this 3 to a 2, you've messed up. Don't do that, because you haven't understood what the formula is. What you actually want to do is you only want to drop 1. What you've actually dropped there, when you swap that to 2, you drop 2 because you dropped it for both tables, right? When you're pipelining, only one of your tables is in working memory. The other one you still have to read in from the hard drive. So if you like expressing the formula in that way, then I would separate it into 3 times by the number of pages in R plus 3 times the number of pages in S. And then if you want to drop your pipeline, you drop only 1. Right? When you have them lumped together, you're dropping it from both. And that is an incorrect way to pipeline the hash join formula. When you separate it out, because basically what you're saying is that rather than reading in all your results and reading them out, you only have to do it once. So this is a more accurate way of expressing pipelining of that formula. Pipelined. All right. If you have questions on pipelining hash join, let me know. All right, now, yeah, ideally, if you can answer some of these questions, they'll help you answer the questions in the exam because you'll actually have an understanding of what that formula represents. Speedy. All right, so hash indexes don't really do range queries. If you look at the formula for a range query and hash index, it's monstrously large. Hash indexes don't do range queries. Okay? Nada. They don't do it. Now, B plus trees, on the other hand, they do range queries and they do equalities, right? So B plus tree indexes can do both range and equality. Hash indexes, they can only do equality. They cannot do range. All right? Now, a clustered index is when the order of the files saved on the hard drive matches the order of the index. Now, that's very important because you can still have ordered files, like you can have a sorted heap file on your hard drive. But if it doesn't match the order of your index, then it's unclustered, right? So the order of the index has to match the order of the files for it to be clustered. And it's usually only really important when it is a B plus tree because clustered files are more performant for range selections. Quality doesn't make much of a difference. Range, on the other hand, that's important. So when you're dealing with clustered or unclustered, it's particularly critical or most noticeable when you're dealing with a B plus tree and you're dealing with a range query. All right, so that brings us to reduction factor. Oh, also compare search key field prefixes and query predicates. So when you're dealing with whether or not to use an index, the order that the index is specified in is pretty important. If you have a query that's like select age and salary, right? Or a query that's a select age, or you have a select salary, right? And then you had an index where the key was age and salary, right? Sorry, let me use that square bracket, baby, angular bracket. Right, so this is your index key, age and salary. Can you run this query on that key, on that search key? Yes, you can. Can you run this query on that search key? Yes, you can. Can you run this query on that search key? No, you cannot. So when you're dealing with a search key for an index, it is primarily sorted by the first attribute, right? So it's all sorted by age first. It puts it into blocks of age, right? And then it will secondarily sort by the second key in your composite search key for your index, right? So if your second key is salary, that means within a block of 19-year-olds, you've got someone making $18 an hour, someone making $24 an hour, someone making $50 an hour, right? And that's all within the age bracket of 19. And then the age bracket of 20, again, you've got someone making $20 an hour, $30 an hour, $50 an hour, and then you have another bracket, etc. But what's really critical about this is that you can use this search key to answer these two queries because it's going to go in and it's going to find the age bracket first. And then if it needs to, it can find the correct salary. This, it can just go in and find the age and the salary doesn't matter. That's fine too. But this one, this index is useless for this query because your salary isn't ordered. Like you can't go in and get all salaries from say $20 an hour to $50 an hour because you actually have to first find the age group and then go into that age group, find all those salaries, and then go into the next age group, find all those salaries. So this search key for your index is useless for this particular query. So when you're talking about the usefulness of an index and a query, pay attention to the order in which your search key is presented. All right. Result size depends on the query predicates. So if your query is age and salary, and your index is age and salary, then you can use both the age and salary to reduce your result size. But if you're only selecting age, then you can only reduce your query size by what you're selecting. All right. So here's an example. We have time, more or less. If we're just going to take a moment to run through this. So you've got a page nested loop join at the bottom, and that is between tables C and B. I'm just going to shift that little doodad. Sorry, I should be able to see this bottom corner. Would you mind just shifting in a little bit over? Nice, thank you. All right, cool. So you've got a join at the bottom between B and C, and it's a nested loop join. And we know from this slide that the nested loop join is being done in okay, so it has not specified what kind of nested loop join. We're going to use page. All right, everyone fine with that? Cool. So we're going to use page-based nested loop join. So first of all, we write up all the information that we know about the tables in this join. This is very important because it makes answering questions later on easier. All right, so we know that A's table has 2,500 tuples, 2,500 tuples, right? And we know that there's 10 tuples per page. How many pages are there? Yeah, 250 pages, right? So we took the number of tuples, we divided it by the number of tuples per page, and that got us the number of pages. Beautiful. All right, and then we have table B. Table B has 300 tuples. All right, and then 50 tuples per page. All right, and that meant that we end up with 60 pages. Is that correct? Yeah, it's just 6. Yeah. 6 pages. Beautiful. And then C has 2,000 tuples. And it has 20 tuples per page. And therefore it has 100 pages. Alrighty. So we now know what each of our tables have. We then get to write down that there's a cluster B plus tree index. Yep, and then And that exists on AID. And the index has 100 pages. All right. Then assume that 2 passes are required to sort. So we know that sort, merge, join is going to require 2 passes. All right. And then for all join results, so whether it's A join B, B join A, sorry, B join C, or C join A, all of these have 10 tuples per page. All right, so then calculate the cost of the following join plan. So let's start with our nested loop join. Who remembers? Okay, so first of all, when we're doing a consecutive series of optimizations, we have to find out, 1, the cost for the first join, but then 2, the result size, right? Because we then use that result size to know how many pages are in the resulting table, and we use that to calculate the next join. So let's start with working out the cost of our first 2-table join. So the formula for working out the cost of a nested loop join is the number of pages in one table, right? So I guess let's have a look. B and C, B is the smaller of those 2 tables. So we're going to make that the outside table. And the reason we're making the outside table is because it's going to result in a smaller cost. Okay? So does anyone know why that works like that? All right, number of pages in B is our smaller table. All right, and then that is plus bracket the number of pages. Now, we're using pages because this is a page-based nested loop join. So the number of pages in B times by the number of pages in C. Right, so that's our formula. And then when we plug in the numbers, we got the number of pages in B, which is 6, plus the number of pages in B, which is 6, times by the number of pages in C, which is 100. All right, so that's going to give us a cost of 606 IOs. Now, please write your units because you're dealing with both numbers of tuples and result size and also IOs for your cost. So this is the cost of that first join. Now we need to work out the result size. So the result size is going to be the number of tuples, the product of the number of tuples times by the product of the reduction factor. All right, so what that means is that we're taking the number of tuples from B, which is going to be 300, times by the number of tuples in C, which is 2000, and then times by the product of the reduction factors. So this reduction factor is based on the join, so we have to be joining C and B. And when we're looking at the product of the reduction factor of a join, it's 1 over the max of either the column in A or the column in B, right? So A and B I'm using loosely. In this case, it would actually be B and C, right? So this column though, the column that we're looking at the maxes is the join column. So we need to look at B and C. We need to go, which attribute would they be being joined on? And we can see from this example up here that C has one of BID as a foreign key. So that means we can assume that when we're joining B and C, we're joining on BID. So that means we also look at then the values of BID. And we know that if BID is the unique primary key, the unique identifier for B, that means there's 300 values of BID. So we can use that 300. All right, so then it's times by 1 over 300. All right, because that's the max of the columns. So that's going to end up with 2,000 tuples. Let me just double check that one. Seems too good to be true. Yep, that is correct. So now that we have the tuples, there's one other really important step when you're calculating the result size. Can anyone tell me what that is? It's a conversion. What are we converting? Yeah, we absolutely have to convert tuples into pages. All right. Now, who knows? This is a resulting join table, right? Like this table represents B join C. Yeah. And who knows how many pages, how many tuples per page B join C has? We talked about at the beginning. When I wrote this up, this was all the resulting tables possible, right? And what is the number of tuples per page? Yeah, 10. So we then take this 2,000 tuples of the resulting table in B join C, and we divide it by the tuples per page, which is 10. So that's going to end up with 200 pages. Now, again, I would highly encourage you to write your units so that you know when you have converted from tuples to pages, and you also know what your ongoing costs are. So your 600 IOs. Right, so now that we've calculated that first join, we then can go and calculate the sort merge join. So the sort merge join, the formula for a sort merge join is, so this is page-based nested loop join. And then there's a sort merge join. And this basically is you sort it and then you merge it. So the sorting is going to be 2 times by the number of passes in a table times by the number of pages in that table, right? And then again, we're going to sort the other table. So the number of passes of the second table times by the number of pages also in that second table. And then we're doing the joining part, the merging part, right? So then we just add the number of pages of that first table plus the number of pages in that second table, right? So in this instance, our first table, it doesn't matter which is inside, which is outside, because this is like a mirrored thing. But what we know is that the resulting join of B join C is currently in working memory. Yeah? Yeah, good. So because it's in working memory, that means we don't need to read in one of these reads in order to sort it, right? So we're going to do 1, and this is going to be B join C, B join C, and then this is going to be A, and then we've got B join C, and then A, right? So when we throw that together, we've got 1 times by the number of passes, which is not table dependent, just period. So it's going to be 1 times by 2 times by the number of pages in B and C, which is, we worked out that there was a 200 resulting pages. All right, and then we've got 2 times by the number of passes, which is 2 times by the number of pages in A. The number of pages in A is 250. All right, and then we're going to add together the number of pages in our resulting table plus the number of pages in our table A. And that will give us the total cost for this sort merge join, which is then end up going to be 400 plus 4 times 250 is 1,000. And then 200, and then 250. So this ends up being 0. Ooh, and then we've got 8, 1, 5. So I think that ends up equaling 1,850. Let's double check that. All right, and then lastly, once we have the 2 costs, this one and this one, we need to add them together, right? Because it's the total join cost of those 2 consecutive joins. So then you'd end up with 6, 5, 4, 2, 2,456 IOs. All right, can we check that? Oh, it's an index scan. Whoop. I have made a mistake. Sorry, gang. So an index scan is going to change the way that we do this. So this was the original sort merge formula using the pages from A as if they were in the hard drive. But we've been told that we're using the index. So I apologize. We're just going to redo this last little bit. All right, so we do the index scan. And the index scan is that means that we're only using the index pages. So we know that there's an index scan on AID. And we know that from the previous slide, B also has an AID. So the join is going to be on AID. And that means that we can just use the index pages because index is on AID, which is what is in both this resulting table from B and also A. All right, so first of all, we want to do the index scan. Now the index scan, we were told that this was a clustered B+ tree. So clustered. So whenever we're dealing with clustered, we know that we're dealing with the number of pages. All right. So then that it basically equates to, you've got the number of pages of the index, and then basically times by the number of pages in the index times by the reduction factor. I'm pretty sure. Let me check. Yeah. So then you've got times by the reduction factor, actually, times by the number of pages in A. Okay, so that doesn't feel right. The reason why I'm hesitant is because if we're doing an index scan and the index scan has the join column on it, like, because I said to you earlier that like the index is on AID, right? And when we're joining this resulting table, right, the only column that we can join this resulting table, so these two on, is going to be AID, right? Because that's the only column that is in table A. So the reason I'm hesitant is because the math that it's showing me is that it's doing an index scan and then also fetching all the pages from A. But that shouldn't be necessary if AID is in the index scan, because that's what you're joining on. Now, if you're returning results, like if you wanted to know the name of AID, then yes, you would need to get the pages. So I'm going to assume, even though it's not explicit in this question, that's what they want. Like they want other columns in A that aren't just AID. So based on that, we're going to continue forward with what they have written. So you've got the index pages plus the number of pages in A, which is going to be the 100 index pages. Wait, it's a plus. Sorry, there's a squiggly line here. Plus the number of pages in A, which is 200, 250. Excellent. And that's going to be equal to 350. And that is going to be in IOs. So that's the cost of the index scan. And then we're going to do the sort merge join, which again follows this formula. And so then we end up with the resulting table plus 2 times the number of passes in table A. I think that should be A's index, but again, I'm not sure. Sorry, hold on. Okay, cool. So we are getting all the tables from the underlying hard drive, but also the thing is that an index is inherently sorted, right? So an index is sorted on AID because that's our key for this index here, AID. So what we actually find out is that this, when we do an index scan on AID, it's already sorted, which means we actually don't need to do this step here of sorting AID because it's sorted based on the index. So that means that when we add these together, we end up calculating the cost of sorting B join C, and we still pipeline that because that resulting table is still in our working memory. So we've got 1 times the number of passes times by the number of pages, which we worked out was the resulting join of B plus C ended up being 200 pages. 200 pages. Yep. So that's going to end up equaling 400. All right. And then we still need to add together those pages from both tables in order to do the join. So then this table, when we do this scan, ends up being this cost, so 350. So then you end up doing your number of pages in B join C, which is 400, plus the number of pages in your A result, which is then going to be 350. So that then equals 750. And then we add those two costs together. So the 750. Yep, so then add these two together. Wait, no, that's what I did. Yep, add those two together, 750, and then add it all together, which then ends up being the cost of the 606 IOs plus 750. All right, let's just go through the answer slide together because I'm getting a bit lost based on this. All right, so we started off by calculating the number of one over the number of keys. So when we're doing the join, and then we worked out that there's 2,000 tuples in our first page, which then equals 200 pages in our resulting pages. All agreed. So then we take the number of pages in table B. So this is actually table B join C. So this is the join cost. So this is the resulting size of the table. This is the join cost of joining B and C, and that is our 606 IOs. Right? And then we took the number of pages in the index of A, the index scan. We added the number of pages of A because we're fetching those from the hard drive. So that gets us 350 IOs. And then lastly, we took the number, we did the number of pages. So this is sorting the resulting table because that would not be sorted on AID. And then we don't have to sort these pages because they've already been. So this one is definitely sorting those. So 2 times the 200 underlying hard drive pages. So because, oh, this is just the translation. Lol. Okay, so 2 times 2, and then the number of pages in the joiner B plus B join C is 200, and then times by 2. So that's your 800 IOs. So that's the cost of sorting that resulting table. And then you end up with the cost of the sort merge join. So you've got the 350 from the index scan plus the 800 from sorting the sort merge join. And because it's in working memory, you don't have to read it into memory. So you drop that last step. And then you end up with 1,150 IOs. And so then the total cost is the 606 plus the 1,150, which is then equal to a total of 1,756 IOs. So apologies. The things that are worth clarifying here is that this cost of accessing A is getting both the index and the underlying hard drive pages and getting every page in that underlying hard drive. And then the sort merge join, the sorting of the resulting table was necessary to happen in full, so we didn't drop it there. Where we dropped our pipeline was when we were joining those two tables after the sort, right? So then that's when, because we had this in working memory from the index scan, that's there, and then this from this table, and then we join those together, right? So that ends up being the total cost for this join. And then lastly, we add that all together to get the total cost for both joins. All right, normalization. So who remembers the 3 phases of normalization, right? So there's first normal form, second normal form, and third normal form. In first normal form, what do we look for to resolve? All right, so when we're in first normal form, we're looking for repeating groups, but I'll give you a bit of context. So normalization is basically about data integrity. In relational entity databases, we basically break down data so that it has high data integrity and it's all semi-separate, right? So we want to reduce data duplication and redundancy. Now, when data is non-normalized, when it's denormalized, we get 3 anomalies. Those are insert, delete, and update anomalies. So when you insert something into denormalized data, you end up often having, like, you can't insert a row where there's only half of the attributes filled in. So you end up having to fill in other attributes, or you can't insert it at all. There's a deletion anomaly where if you delete, let's say, 2 particular rows, then you end up losing out on something else. So one example is that you have like doctors and patients, and they might all be in a denormalized data row. And if you wanted to basically delete one patient, if that doctor is the only person that sees that patient, then you may end up losing that doctor because you had to delete the patient, but because you've denormalized data, it's not separate data, it's all in the one row and you lost out on data that you should have otherwise kept. And then lastly, you have the update anomaly, which is basically when you go to update data, you might update one row, but because that doctor may have multiple patients, if you only update the one row, you may miss other rows where you should be updating that doctor's information, right? And then you have inconsistent data. So normalization is the process of taking larger denormalized tables and breaking them down into smaller tables. So the way that we take them and break them down to smaller tables is getting into first, second, and third normal form. So first normal form is removing repeating groups. The second normal form is removing partial dependencies. So a partial dependency is where part of the key is determining another attribute. Not the whole key, but part of the key. And then the last one is third normal form, which is to remove transitive dependencies. So when you're removing transitive dependencies, that's when a non-key attribute is determining another non-key attribute. So to achieve first normal form, we remove the cells that have multiple values inside of them. So if anything looks like there's a list, you gotta break that out, break that down, and move that around, right? So one example is order item might be one column in your Excel spreadsheet, but in that column it has a customer and it has this kind of like a nested repeating group. So the order and the customer has one value, but then the item, description, and quantity, there might be 3 or 4 of those, right? So you've got this kind of repeating group pattern. So you have to break that out into its own table. So these brackets denote that there's a repeating group just here. So you just break that out into its own table. So you would have item, description, and quantity into its own table. And you would also carry over one of these. So it might be the order or something so that you can link them back up later. Then to achieve second normal form, you remove partial dependencies. So as mentioned, partial dependency is where part of the primary key, so partial dependencies really only happen when you have a composite primary key. Part of that key is determining a non-key attribute. All right, so an attribute depends on part of the primary key, but not the whole primary key. And then lastly, you have transitive dependencies, which is where a non-key attribute depends on another non-key attribute. All right, so So when let's normalize this to third normal form. First of all, let's start. Is it in first normal form? Yes, it's in first normal form. Generally, when you're presented with this style of table, it will be in first normal form. I guess if you're particularly concerned, you just have to look for potentially like nested brackets. But generally speaking, this way of presenting a table is always going to be in first normal form. Just do a quick double check. All right, and then in first normal form, we can see that there is a composite primary key here, right? So order ID and dish ID are underlined. That identifies it as a composite primary key, right? These two columns are uniquely identifying this whole row. And we can see that, so the meals ordered table has a composite primary key. We're then given the 3 functional dependencies. Order ID is determining customer ID and customer name. Customer ID is determining customer name. And dish ID is determining the dish and the dish price. Right? So we need to break this down into smaller data tables. All right, so first of all, let's talk about, we've worked out it is in first normal form, so second normal form. We're looking for partial functional dependencies. Can anyone identify a partial functional dependency? So if we look at the previous slide, we can see that there's a composite primary key. So what are some things that are dependent on one or the other of these, but not both of them? So we know that order ID is determining customer ID and customer name. Yeah? Order ID is part of this primary key. So we know that we're going to have to separate this out. We also know that dish ID determines dish name and dish price. So I'm going to start there in that dish ID, dish name and dish price should be taken out because it's a partial functional dependency, right? So we end up having a table, dish ID. So we'll have dish, right? And dish will have dish ID, dish name, and dish price. All right, and then now that we have dish, we then have our original table, which is meals ordered. Right? So we've still got order ID, customer ID, customer name, and then dish ID. Now, the thing is, whenever we separate out a table, when we're normalizing it, we keep an ID so that we can link them back up, right? So we did create this table with dish ID in it, but dish ID stays in both tables, right? We move out dish name and dish price, that goes into its own table, but we keep dish ID. So this is one partial functional dependency resolved. Now, order ID determines the customer name and the customer ID. That means that we can also take out order ID determining customer ID and customer name. So we're going to have an order table. An order table. And this order table is going to have the order ID, then the customer ID, and the customer name. All right, and that means that we then move these two out of that table as well. So meal ordered, we move those out of that table, but we keep that ID, right? We always end up duplicating like the connecting ID, right? So we keep order ID and then dish ID. All right, so that is going to be second normal form. Are we finished? No, we're not finished. So what we then have to do next is get it into third normal form, right? So this is second normal form. And now we've got to go to third normal form. In third normal form, we remove transitive dependencies. And a transitive dependency is when a non-key attribute determines another non-key attribute. So we know that this is a non-key attribute. Sorry, this is a key attribute. This is a key attribute. These are key attributes. So we're looking at a non-key attribute. Who can see a non-key attribute in one of these tables? Yeah. So we're told that this is one of our dependencies, that customer ID determines customer name, right? In our tables so far, customer ID is a non-key attribute, right? Like it's just a regular attribute and it's determining another non-key attribute. So this means that in third normal form, we have to separate these two out, right? So then we update it where we'll have customer, right? And this will have your customer ID and your customer name, right? And now we remove customer name from this table, but we keep that linking ID, right? Yeah. So that then brings us to third normal form because we've removed both partial functional dependencies and transitive functional dependencies. All right. So that can be seen there. All right. Next. We'll wrap up shortly. So transactions, basically transactions need to follow the ACID principles, which are where it has to be atomic, consistent, isolated, and durable. So there's 3 different problem anomalies that happen when transactions are not atomic. Those are the lost update problem, the inconsistent data retrieval problem, and there's one other. Can you click this slide? Yeah, so this one is the inconsistent data retrieval problem where Alice is summing a series of rows and Bob is simultaneously trying to update some of those rows. So when Alice does this summation, she's going to get some rows that have been changed and some rows that have been unchanged. And that means that she's retrieving inconsistent data. That's why it's called the inconsistent data retrieval problem. So if you click space again, there should be a table on the next page that kind of illustrates that in further detail. Yep, so as we can see, Alice is trying to sum all these salaries together. Some of the salaries she sums are after Bob has updated that salary. But then some of the salaries she sums are before Bob has updated that salary. So that is where it's inconsistent data retrieval. So this price here is false. It either should have been all done before Bob started updating salaries or all done after Bob started updating salaries. So that's why those ACID principles of atomic, consistent, isolated, and durable are really important, because if this happened in isolation, then this wouldn't have happened, because Bob, well, more specifically, Alice wouldn't have been able to see any of Bob's updates until they'd all been done. All right, next slide. All right, and so then this, yeah, so this is, it should have been one or the other, but instead they were intermingled, which is the problem. Space. All right, so a DBMS which strictly implements ACID compliant transactions can never encounter the inconsistent retrieval problem, which is what we've just talked about. Which ACID property is primarily responsible for preventing this problem? Explain how it prevents the inconsistent retrieval problem. So I kind of gave that one away, because if they had been isolated, then that wouldn't have happened. The other ones also obviously play into it, like atomic, consistent, durable, but isolated specifically when it comes to the inconsistent data retrieval problem is the issue. Yeah, so isolation guarantees that concurrent executions of transactions, so concurrent being more than one at the same time, leaves the database in the same state as if transactions were completed sequentially. So it makes a choice about whether or not to act as if it's happening before that transaction or after that transaction, but just never like during. All right, distributed database systems. Yep, so distributed databases are when you need a certain scale or global availability. So obviously we have a lot of data giants in the world. You've got your Metas, you've got a bunch of other things. So the pros are they're scalable, they're available and reliable, and they have better response time for localized data. So if you're a user of Meta in the US, you might have servers that have your data in Texas. And if you're a user of Meta in Australia, they might have servers with serve your data in Sydney. And that way it's actually faster for you to get your results, because it's actually literally traveling less distance. Sure, it happens really quick, but it still affects the return time. The cons is that distributed databases are more complex and there's CAP trade-offs. So CAP is basically the consistency, availability, and partition tolerance. So there's like a Venn diagram for CAP. C-A-P. So when you're dealing with distributed databases, you've chosen participation tolerance, right? So this one, you have to do it if you're having a distributed database. Your next choice is then, do you want consistent data or available data? So do you want PC or CP or AP/PA, right? Now, in distributed databases, you need partition tolerance, so you can't really have this spot here, right? Not in a distributed database anyway. And this middle point doesn't exist. There is no perfect distributed database system. This middle point doesn't exist. So your choice is either this one or this one, right? So high availability and partition tolerance means that the website or your application will always respond to users, but it might respond to users with slightly outdated data, right? So the example is if you're accessing Facebook and then your friend in the UK posts their summer pickies and is like, oh my God, and you comment and you're like, so cute, girl, right? So you might then tell your friend like, hey, like I commented on your picky, it looks amazing. Your friend might refresh their page and they might not see your comment, right? So then they'll refresh it again and then they do see your comment. So even though you knew that you'd left that comment and your friend couldn't see it at the time that you had left that comment, that's a good example of high availability. Your friend's Instagram app was available for her to look at her own post and see the comments on it, but it was giving her outdated data. Now, when she refreshed it, she did get your data. So it's not that you don't get the data at all, it's that it's called eventually consistent, right? It's not immediately consistent, it's eventually consistent. The contrast to that is CP, which is consistent and partition tolerant. So consistent means that basically your application or web page will basically block until everyone has the exact same information, right? So there may be some, I don't know, high integrity data systems that really require consistency. Like if people are moving large sums of money, like you don't want to transfer 16 grand and then potentially not see it in the bank account of who it should be going to, because then you're like, did I just lose 16 grand or did I transfer it to the wrong person? I don't know. So consistency is about serving the right data and making people wait for it. Availability is about serving people whenever they want, but it's not necessarily the most up-to-date data. All right, so distributed databases, you've got centralized, partition, and replicated. So partition is where they're like splitting up different data sets across different data centers. Replicated means they're just duplicating all the same data for multiple points in the world. Centralized means you just have the one and it's not distributed. Yeah. All right, so this is an example of trying to decide what kind of database partitioning strategy this client should use. We're probably just going to keep going in case there's other things. Distributed solutions, horizontal partition, yep. NoSQL. All right, so NoSQL, you've got four families of NoSQL databases that we looked at in the subject. Does anyone recall any of those four? Yep, graph is one of them, correct? Yep, key value store is another one, yep. Yep, document store is another one. Yep, and column family. Yeah, beauty. So those are the four: column family, key value, document, and graph. So what is the strength of a key value store? It can store anything as the value, and that includes multimedia. So images, videos, other documents, whatever you want, right? So that's very important about a key value store. It can store any kind of value as the value, and that includes other media, right? What is the like pro or con of a document store? So a document store is most often done in, say, JSON and XML, not always, but most often. And it is essentially kind of like a key value store under the hood, except for the fact that it cannot store multimedia in the way that key value store can, right? Because it's a document store, it's being saved as a file on your computer. And that means that that file itself can't then have like an embedded image. It's not like a Word document, unfortunately, right? So you can't have multimedia in a document store. All right, then let's talk about graph. What is a graph particularly good at? Yes, graph is excellent at capturing complex relationships, right? So graph has a series of nodes, that's your data points, and then it has a series of relationships or edges, and those edges can also have information, and it helps you map complex relationships when looking at stored data. And then lastly, we have column family store. Does anyone recall how column family store works or what it's good at? So a column family store is probably the most similar to a relational entity database. And a column family store basically means that your rows and the columns that are in your rows are determined by row. So usually we talk about the columns in a row being determined by the table as a whole, and all of those rows have to have all of those columns, right? But in a column family store, it's much more flexible. You can basically determine how many columns and what those columns are, what the data types are by row within what we call a column family store, which is kind of like, within what we call a column family, which is equivalent to a bit of like a table, right? So within one table, column family, your rows are determined by row. Sorry, your columns are determined by row, not by table. Yeah. Cool. So generally we use NoSQL for very large databases because they perform better. So if you are storing relational databases and you have to store those columns for every single row, but let's say then those columns are empty for a lot of your values, you still have to set up those columns and you're still taking up space in your hard drive for those columns, but you don't need to be storing them. So you end up with just like a lot of like, it's just not very performant, and it's much more efficient to be using some of these other NoSQL type of databases because they're more scalable, they do a bigger volume. Yeah. And they're also more flexible, and that means you're storing only what you need and less of what you don't need. All right, and then, yep, so key value, document store, column family, then graph. Yeah. All right, so then FaceTube wants to do a thing. We'll just skim over this question. I feel like you guys will get a copy of these slides, so if you want to run through these questions in your own time, highly recommend it. And then, yeah, questions and answers. Does anyone have questions about the subject? Cool. All right. Yes. In the exam, the good thing is like, okay, so the thing that I noticed a lot, at least with marking assignments, was people got really confused around crow's foot notation. So I think that's something that's very hard for people. But I think because your exam is digital, you won't be asked to draw crow's foot. You'll just be asked to interpret it and understand what is happening in crow's foot. So I wouldn't worry too much about that. Other than that, obviously, query optimization is not incredibly complex so much as it requires you to keep track of a lot of different numbers and to really understand how those formulas are working under the hood. So I think query optimization, it's good that they make your mid-semester on it because I think that it forces you to actually learn that content fairly well. I think also in your note sheet, I would just note down, like, okay, so one of the things is like, I'm fairly sure that you will be asked about some kind of transaction issues. So remember we talked about how you have to have the ACID principle, and then there's like 3 different scenarios that happen when you don't have the ACID principle, which is your lost update problem, the inconsistent data retrieval problem, and then there's the lost update and the, keep forgetting the third one. But there is 3, and I would highly recommend that you know at least one of them. I'm not sure what kind of questions you'll be asked on your exam, but I know that that is something that we definitely touch on. I also know that I recall being asked about locking. And it might just be in a broad high level term, but you should be able to know what locking is in a database and what levels and granularity it can be done at. The exam is very long, so I would highly recommend that you move fast through the exam. And that also brings me to my last point, which is like, please write your own notes. I understand that it's very tempting just to print off all of the tutorial, like questions and answers and then all of like the lecture slides and then be like hefting through this book. But because the exam is generally speaking long, it kind of separates those who were constantly checking their notes from those who actually spent the time to learn the content. And that's why I'd highly recommend that you write your notes for 2 reasons. 1, because it will actually force you to study for this subject. Shock, horror, I know. But 2, it also then helps you understand where in your notes you've written certain information so that if you do end up needing some help during the exam, you have a clearer idea of where to like find that information in your notes rather than just taking in someone else's notes and then having to like flip through them frantically. So yeah, I would highly encourage you to write your own notes, obviously study, and it's pretty safe to assume that almost like every aspect of this course will be touched on at some point. Maybe not in great depth, but like it's a big exam. It's all in there. At least from previous years. That's all I can say. Yeah. No, I'm so sorry. I don't know how many pages the exam was in previous years, and oh, the notes that I wrote. My notes? They're like 20 pages. Yeah. Yeah, they were double-sided. I think it was like 21. Yeah. But again, I like my notes, I broke them down week by week and then I did subject by subject and blah, blah, blah. And yeah. So, you know, do your own notes that will work for you. Yeah. There's no sweet spot. Like if you need more notes, like take more notes. If you need less notes, take less notes. It's up to you. But yeah, just actually revise the content. And I think by forcing yourself to write your notes, you do that. So yeah. Any other questions? Yeah, so I think that's what Abjay was similar asking, like, what is the trickiest aspect of this subject? Yeah. I mean, it varies from person to person. I do think, I don't know. I feel like everything that we learn in this subject is both can be tricky to some, but also is entirely learnable. And what I mean by that is like Chen's, in terms of a diagram language, is quite foreign. But I feel like most people would be fairly comfortable with Chen's by now, right? Like you're like, yeah, it's pretty comfy. And then crow's foot, I feel like that one is potentially slightly more challenging because you're expected to cover that more in your lab work. And if you're not reaching out for clarification, you don't necessarily know how well you understand crowsfoot. So I do understand why that one trips people up. In terms of like query optimization, again, please write the units. I feel like lots of silly mistakes are made when you don't write the unit and then you get confused about which number meant what. Also, always check the tuples per page. That's really critical too, because you will be using that to convert things. That's a really easy mistake to make. In terms of like transactions and normalization, I think normalization is fairly, like I enjoyed that part of the course because I feel like second, third, easy. But again, it's very individually based. I can't speak to what I think is like genuinely the objectively hardest part of the subject. I really struggled originally with query optimization and I had to work pretty hard over my mid-sem to like wrap my head around all the formulas and yeah, get that back under wraps. Great. If anyone has any questions, you can ask Linga or I. And yeah, if you have feedback for the thing, please, yeah, give us your feedback. I'll hand over to Stanley.
Okay. So thanks everyone for attending. Please scan these QR codes. One is to join CISSA and the other one is for the feedback form. And yeah, so first scan this and we're gonna share the QR code for the presentation slides in just a minute. And yeah, thank you to Lucy very much. It was great.
Yeah, I have it here. Yes, I'm screen. Yeah, this is the QR code for the slides. Very good. Oh, yes.